So to understand or to discuss how we can compute the modes of the kernel density estimator function, we'll just like to summarize the idea behind doing so. So in the previous lectures, we learned that we have the dataset D of m data points xi, where each of the data points xi is an n-dimensional real vector. And we assume that this data set is generated by some underlying probability density function p of x, but we do not know what this probability density function is. So we would like to estimate it using the kernel density estimator function f of x. So we have f of x parameterized by h, which approximates the underlying density function, is given by ckn over mh to the power n, sum over all I goes to 1 to m, kernel function k of norm of x minus xi over h square. So this kernel density estimator function, to evaluate the density at any given point x, adds up the contribution of the kernel densities. There is a densities defined by the kernel function k around each of the data points xi. So we have these kernel densities around each of the data points xi in the data set. So the kernel density estimator sums the densities around each of the data points xi in the data set to compute the density at any given point x. So as we discussed in the previous lecture, this parameter h is known as the bandwidth parameter, and rather than going with the full parameterization matrix h, we assume that matrix h is proportional to the identity matrix where the proportionality constant is h square. So by using this and by using the definition of the generalized kernel function in the generalized formulation of the kernel density estimator function, we arrive at this formulation of the kernel density estimator function with a single scalar bandwidth parameter. So this is a single scalar hyperparameter of this entire kernel density estimator function. So as we discussed, the modes of this density function denote the region of high densities in the underlying probability density function. And since we do not know this function directly, this probability density function, we approximate it with our kernel density estimator function f of x. So this is a plot of f of x at any point on the real axis. So as we discussed in the previous lecture, the natural question is like, how do you find the region of high densities in the dataset or the clusters defined by those high density regions? So basically, here's a one set of cluster of points over here. There's another set of cluster of points over here. So the modes of this density function are going to give us the clusters in the underlying dataset. So one natural question is, how do you find the regions of high densities or clusters defined by those high density regions? So we know that the modes of this density function denote the region of high densities or clusters in the underlying dataset. So by finding the modes of the kernel density estimator function, we can find both the centroids of the clusters as well as the clusters associated with those modes or centroids. So the natural question is, how do we mathematically do it? So mathematically, how do we do it? So let's take any point on this x-axis. So let's suppose if we select this point, then the gradient at this point points in this direction. So if we move in this direction, then we are going to arrive at a point of higher density. We can again compute the gradient over here, and perhaps this gradient will take us to this point which has higher density. Again, so on by repeating this process. We can arrive at the mode over here. At this point, if we compute the gradient will point in this direction. So naturally, if we start from this point, then this point will move in this direction. So if we start with any point in this region, it will point in this direction, and for any point over here will point in this direction. If we go beyond this point, then we'll start moving in this direction. Similarly, if we go beyond this point over here, we'll start moving in this direction. And similarly over here, any point on the left will take us in this direction. So now we do not know the underlying probability density function P of x. So we do not know this, but we know a function, an analytic function f of x, which approximates this underlying probability density function over the dataset D. So we can use this function as a proxy for the underlying density function, and by computing the modes of this density function, we essentially compute the modes of the underlying probability density function that generated the dataset. And we do not have the information about the original density function, but we know a function that approximates this. So by computing the gradient of the kernel density estimator function at any given point, we can find the mode associated with that point. So for example, if we take this point and if we compute the gradient will point in this direction. Similarly, eventually starting from this point will converge to this mode over here. We take any point in this interval. So if we take any point in this interval and if we compute the gradient, eventually by following the gradient will eventually arrive at the mode associated with that region. Similarly, let's take this region for example. So in this region, if we start from, we can select any starting point for that matter. So let's suppose we pick this point as our starting point. We start computing the gradient eventually. So if we follow the gradient from this point, it will eventually take us to the mode associated with this region. So the mode associated with this region is over here. So any point in this interval will converge to this mode. So basically, by computing the gradient of the kernel density estimator function f of x parameterized by h, we can compute the modes of this kernel density estimator function and essentially the modes of the underlying probability density function as well. And each of these modes has a region in the dataset such that any point in that region converges to that mode. So any point in the dataset that falls in this region will be associated with this mode M1 over here. Similarly, any point in this region, so any point in this region will be associated with this mode M2 over here. And this is the fundamental idea behind the mean shift algorithm. So the mean shift algorithm uses a mean shift vector to compute the modes of the underlying probability density function or the modes of the kernel density estimator function. So the mean shift vector is actually the gradient of the kernel density estimator function. So this is the fundamental idea behind the mean shift based clustering algorithms. What we are doing is that we started with a data set. We want to cluster that data set. But as we saw in the previous lecture for the k-means algorithm, we have a parametric algorithm where the number of clusters have to be specified. In the mean shift algorithm, we don't have to specify the number of clusters. So to be able to cluster the data set, we would like to find the modes of the distribution that generated the dataset. But since we do not have access to the distribution or the density function that generated the dataset, we approximate it with the kernel density estimator function. And by computing and following the gradient of the kernel density estimator function, we compute the modes of the underlying density function, and essentially we compute the clusters in the dataset. So this is the fundamental idea behind the mean shift based clustering algorithms. So the mean shift algorithm is a mode seeking algorithm. We are computing the modes of the underlying density function by computing the gradient of the kernel density estimator function. So as we can see, we don't have to specify the number of clusters. We can just pick any point and just compute the gradient at that point of the kernel density estimator function and follow the gradient thereafter. And that will naturally take us to the mode associated with that region. Now the question is like, what point should we start from? So we know that we have m data points in the dataset D. So we can start from each of the m data points as our initial point, and whatever modes those data points are associated with, the gradients will take us to that mode. And thus the mean shift based clustering algorithm, where the mean shift algorithm uses a mean shift vector, where the mean shift vector is an approximation. It's not the actual gradient, it's an approximation of the gradient of the underlying kernel density estimator function. So by selecting any of the data points in the dataset and by following the gradients thereafter or following the mean shift vector thereafter, we can find the mode with which that data point in the dataset is associated with. So we don't have to specify the number of clusters beforehand. The algorithm automatically finds the number of clusters as well. So whereas in the parametric clustering algorithm, like in the k-means clustering algorithm, we had to specify the number of clusters. In the mean shift based clustering algorithm, we can assume that initially each of the data points is their own cluster. So we assume that each of the data points is their own cluster, and by using some mathematical trick, we eventually, as the algorithm converges, we shrink the number of clusters that we have, and each of those independent clusters corresponding to each of the data points in the dataset eventually merge with each other, and in the end we are left with the ideal number of clusters in that dataset. So in that sense, the mean shift clustering algorithm is a non-parametric clustering algorithm because the number of clusters doesn't have to be specified, and the background theory behind the mean shift algorithm is a kernel density estimator. So now we will derive the mean shift vector. So we'll derive the mean shift vector for clustering the dataset, where the mean shift vector is derived by computing the gradient of the kernel density estimator function. So now you would know like why did we cover all the background theory behind the mean shift algorithm. So eventually, to discuss the mean shift algorithm and the fundamental idea behind the mean shift clustering and the mean shift segmentation algorithms, it was necessary to discuss the underlying theory of the kernel density estimation. So now we will derive the mean shift vector and the mean shift clustering algorithm, which is a non-parametric clustering algorithm. There's a number of clusters, doesn't have to be specified beforehand.